So let me do the second part of the rotational motion lesson, wherein the first one is about a relationship between torque and moment of inertia. Moment of inertia is mr square. The torque is equal to force into perpendicular distance r cross f. Okay, so r cross f, and f can be written as m into a, and linear acceleration is r times angular acceleration. A is equal to r alpha. So then r into m into r alpha is mr square into alpha. Mr square itself is I, and hence torque is equal to I alpha. This is the relation between torque and moment of inertia. T is equal to I alpha. The second derivation I taught today is the relationship between angular momentum and moment of inertia. Moment of inertia is mr square. Angular momentum is again r cross p. R cross p. And r cross momentum itself is mass into velocity. Since linear velocity is r times angular velocity, substituting back here, m into r omega, and mr square itself is I, so I omega. L is equal to I omega. This is the second formula. L is equal to I omega. And angular momentum is moment of inertia times angular velocity. L is equal to I omega. Okay, so the next derivation that I want to teach you is about conservation of angular momentum. Okay, so supposing, in the absence of external force, angular momentum is conserved. In the absence of external force, linear momentum was conserved. We did that. L is equal to torque is equal to dl by dt is the formula which you already know. And in this, if the external torque is 0, then the angular momentum has to be a constant. L has to be a constant. And L itself is I omega. This initial momentum is I1 omega 1 should be equal to I2 omega 2. The initial momentum of the body should be equal to the final momentum of the body. So the momentum has to be conserved provided there is no external torque acting on it. Provided there is no external torque. Okay, that's very important. Conserved. That's known as law of conservation of angular momentum, which states that the momentum remains to be conserved provided there is no external torque acting on the rigid body. Okay, so let's go to the next one. As a simple example of the conservation of momentum is this example where the man carrying a heavy weights in hand standing on a rotating table. There's a rotating table here. A man is standing here, okay, and he is keeping his hand stretched, and he's having some two weights here, and is spinning about his head in an anti-clockwise direction. Okay, in that case, this is radius r1. The same man can stand on the same rotating table with his hands so much closer to his chest such that radius is smaller. R2 is lesser than R1. In that case, he will spin faster, whereas here he will spin slower. This results in a slow rotation, whereas this results in a fast rotation. That is, that I1 omega 1 in this case. Let's talk about I2 omega 2 in the second case. Okay, moment of inertia is mr square. Okay, mass remains the same. R1 square is radius here and omega 1. Mass of the same man and R2 square and omega 2. Here the radius is increasing, so angular velocity will decrease. Here the radius is decreasing, the angular velocity is increasing. That's why it resulted in fast rotation here and a slow rotation here. And this adjustment goes on because initial momentum has to be equal to final momentum. Whether the man is keeping his hands stretched or is keeping it closer, the momentum is going to be conserved. So then, therefore, your radius is increasing. I omega, the angular momentum is conserved. This is an example of angular momentum conservation, which happens by the adjustment of the radius. Radius is small, the angular momentum is more, angular velocity is more, and radius is larger, angular velocity is less, and so it gets adjusted accordingly. Okay, so that's one example. And you can also imagine a ice skater. An ice skater, they're doing ice skating, dancing and all, no? Where they keep both the hands together when they're spinning. When they're spinning around, they'll keep the hands so closer to the chest. But when they are skating around freely, One hand will be there, another hand will be here, and the person will legs also will be like this, and they'll spin around. Then when they're spinning slowly, and they're spinning slowly like that, when they're spinning fast, 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 they're holding it, which no, which shows that the radius is smaller. That's another example that I would like to tell. Okay, so next is this is about ice skater. The third example is about a diver. There's a springboard. There's a board, springboard, from which a diver is going to jump into the swimming pool. Someone who jumps into the pool, he should splash less water. In Olympic Games, you have seen that, which means the velocity has to be lesser. The velocity has to be lesser. When he actually tries to jump, he curls his body like that and takes a dive. He actually somersault. He does a somersault on the air. Okay, and by curling his body so that he gets a radius which is smaller. The radius is smaller. We all know that angular velocity will become larger. And then just about when he enters into the water, he stretches his body like a larger curve and he jumps into the water. So the radius is bigger, the angular velocity is lesser. Thus, when he gets into the pool, he splashes lesser velocity. So I hope you understood. This splashes lesser water, and that's the concept. So that is happening because of the momentum being angular momentum being conserved. So let's go to next term. This is what you're going to write, or write a note on the conservation of angular momentum. This is the notes you're going to write. So let's talk about a rolling motion. Okay, there are two types of motion. Okay, let me talk about a rotational motion, and consider an inclined plane in which there is a cylinder. This is a cross section of the cylinder. The cylinder goes like that at the other end, on the, what to say, it will be on the other side. You can't see that. When viewing from here, you get to see only the circular part. And as you know, the mg is going to be acting downward. This is theta. So this will also be theta, and therefore this will be mg cos theta. And you will have a normal reaction which will be right above this head, but let's call it as n. Why am I calling it as not r and n? Normally I will call it normal reaction as r. Here there is a frictional force which is going to pull it in this direction. The acceleration of this is going to be happening in this direction, mass into acceleration. So then therefore there will be a vector component which is mg sin theta. As you know, this is mg cos theta and mg sin theta. And there is a frictional force. Can you see this is the radius? And the radius and frictional force are perpendicular to each other. Radius capital R of the cylinder. And you should know that this cylinder is going to roll without slipping. It's going to rotate without slipping. If it's got to roll without slipping, the friction has to be more. Okay, and the torque which is responsible for rotation will be R and F into R. R cross F, which is frictional force into R. Torque is also I alpha. Therefore, you can equate both of this. And an angular acceleration is linear acceleration time by R. Linear acceleration is R times angular acceleration. So angular acceleration is A by R. So F into R. So a frictional force is I by A by R square. I into A by R square is the friction force. Why do I do this? If this is MA, then obviously mg sin theta minus frictional force will be equal to MA. And mg sin theta minus frictional force is equal to M into A, where you got a formula for frictional force which is IA by R square. Substituting this here, plugging it in, is equal to MA. Cancelling the M and M, you can write a M here. Mr square itself is moment of inertia, so it's convenient. A g sin theta is equal to A plus IA by Mr square. So if you take a A out, 1 plus I by Mr square, okay, is a g sin theta. Hence A itself is g sin theta by 1 plus I by Mr square is the formula for the acceleration for this cylinder to roll down. So then there will be questions such as this, in an inclined plane, there is a cylinder which is going to roll down. It's a solid cylinder. If it's a solid cylinder which is going to roll down, the moment of inertia of the solid cylinder, this I of the solid cylinder is mr square by 2. As you all know, the moment of inertia of solid cylinder is mr square by 2. On substituting that here, A is equal to g sin theta by 1 plus mr square by 2 mr square. So mr square get cancelled. So A is equal to g sin theta by 3 by 2. So A is equal to 2 by 3 of g sin theta. You get this to be your A. So this is what is the acceleration with which it's going to come down. So this is for a cylinder. Supposing it's not a cylinder, it's not a solid cylinder, supposing it is a sphere which is rolling down. A sphere, a solid sphere. You all know the moment of inertia of a solid sphere is 2 by 5 mr square. You are supposed to know. If you know that, okay, then you can substitute here A is equal to g sin theta by 1 plus mr, moment of inertia is 2 by 5 mr square by mr square, because I by mr square, my moment of inertia I itself is 2 by 5 mr square gets cancelled. You take an LCM, it will be 7. So 5g sin theta by 7. Okay, if you compare this and this is 2 by 3 which is 0.6, maybe 5 by 7 which is 0.77 or 49. So can you see the acceleration of a sphere is greater than the acceleration of a cylinder? Therefore, the sphere will tend to reach down faster because its acceleration is much larger than that of the cylinder. We can, like that, you can compare a ring or whatever you want. So this formula is very critical. Okay, so let me continue with what I was doing. If they ask you to find the frictional force, you know this is the crux of the formula. Mg sin theta minus frictional force is equal to m into A, from which you can write mg sin theta minus F is equal to m into A. So F itself is mg sin theta minus ma. You already know, you found what is A for this kind of a cylinder, which is solid cylinder. It's 2 by 3 g sin theta is equal to F. So you can subtract this because it's mg sin theta, 1 mg sin theta, 2 by 3 mg sin theta is nothing but 1 by 3 mg sin theta. That will be the value of the frictional force. So that will be the value of the frictional force that you get. And supposing you want to find the coefficient, you know frictional force is equal to coefficient of friction into normal reaction, which is n. So mu is equal to F by n. You know frictional force itself is 1 by 3 mg sin theta. And the normal reaction according to this diagram, n is equal to mg cos theta, opposite vectors, so mg cos theta. So mg get cancelled, so it's 1 by 3 into tan theta. Tan theta by 3 will give you the coefficient of friction. So like this, then it's about supposing you have two types of motion in this. So then therefore the coefficient of friction has to be greater than or equal to 1 by 3 tan theta if it has to have a motion which is rotational without slipping. So let's go to, you know that supposing cylinder is going to roll down, it's having a rotational motion as well as translatory motion. The two types of motion, one is rotational, so there's a rotational kinetic energy plus a translatory kinetic energy, straight line motion, both of which will contribute to total kinetic energy. Rotational motion, you know the kinetic energy formula is half I omega square, and the translatory motion kinetic energy is half mv square. We want VCM, center of mass. Okay, we know that angular velocity is linear velocity is r times angular velocity. So angular velocity is v by r. So substituting that back here, half I v square by capital R square. Let's keep it as capital R square instead of, because the radius of the cylinder is capital R. And you can write the moment of inertia of this solid cylinder itself is mr square by 2. Write it as, don't write mr square because r square and r square is getting cancelled. So instead write mk square, because a general formula for moment of inertia is mk square, where k is the radius of gyration. I am sure you remember what is gyration. A v square by r square. Okay. So when you do this, plus a half m vcm square. So you can see a half m v square is common now. Okay, vcm square. So half m vcm square is common. You get a 1 plus k square by r square, because you can calculate the k, radius of gyration, for every rolling object or spinning object. So this is the formula, general formula for total kinetic energy when it comes to rotational and translatory. So if you know the linear velocity and you know the radius of gyration and the radius of the rotation, you can find the total kinetic energy. Or in other words, you can know this formula also, anything you know, so that you can substitute and get this answers. Okay. So bodies, a ring, a solid cylinder, and a solid sphere are falling down. So let's see, three bodies. One is a ring. Next is an inclined plane. You have a solid cylinder, which is what we saw now, and it's a solid cylinder, okay, and a solid sphere. Solid sphere. Which of this will? They're all starting from rest, which means u is equal to 0 for everything. And it's going to slide down this inclined plane. Which of the bodies will reach the ground faster and will have maximum? Which of these will have maximum velocity? With maximum velocity. Okay. The question is, okay, if it's going to talk about which is going to reach faster, we all know that, okay, which one will have maximum velocity? Okay, the only way to do the sum to find the velocity at the end of the journey is mgh, the total potential energy, is equal to the kinetic energy, which is equal to mgh is the potential energy lost, which is equal to the total kinetic energy, which is rotational motion as well as translatory motion, whose formula you got it here is half mv square, half mvcm square into 1 plus k square by r square. If you know the radius, you know the radius of gyration, you can substitute there. So then the m and m get cancelled here. So you can get a formula for velocity. The v velocity itself is velocity square itself is 2gh by 1 plus k square by r square, and a vcm itself is 2gh by 1 plus k square by r square. Okay, you can calculate what is radius of gyration for each and every one. Say for example, in this case it's a ring. What is the moment of inertia of the ring? It's mr square, which can be equated to mk square. So then therefore a k square is equal to r square. So then you can write it as r square itself, and r square get cancelled. So it will become 1. So it will be 2 and 2 get cancelled. VCM itself is gh for a ring. So done. So let's go to next one, which is a solid cylinder. The same formula, VCM is equal to root of 2gh by 1 plus what is the radius of gyration of the solid sphere? What is the moment of inertia of a solid sphere? Solid sphere is like a disk, which is mr square by 2 is equal to mk square. M and m get cancelled. So k itself is r by root 2. K itself is r by root 2. So a k square is obviously r square by 2 by r square is cancelled. So root of 2gh by 3 by 2. So make it 4. And so you get this is for a sphere, VCM of a sphere, solid sphere, solid sphere, and it is 1 point something. So this is definitely solid sphere is greater than the ring. So let's talk about what is it? Oh, this is a solid cylinder, is it? Okay, this is for a solid cylinder. I'm sorry, cylinder. I wrote it as solid cylinder, mr square by 2. Let's talk about a solid sphere. Moment of inertia is 2 by 5 mr square is equal to mk square. M and m get cancelled. So k square itself is 2 by 5 mr square. So VCM is equal to root of 2gh by 1 plus k square by r square, where k square itself is 2r square by 5. 2r square by 5, where this and this get cancelled. So it becomes 7 by 5. When you take it up, it will become root of 10gh by 7 by 7. 10 by 7 is 1 point something. So can you see this is for a sphere. The sphere has got the maximum velocity. The sphere is what is having the maximum velocity when it comes down. The least velocity, okay, among the three bodies, the sphere has the greatest velocity when it gets down, and so the sphere also will have the maximum acceleration. The ring has the least velocity, and this sum is very, very important. Either you do it like this, or you can even do it. This is one way of doing it. Another way of doing it is you can find here they've asked for the velocities at the end of the journey. So the only way I can do the sum. I can also compare their accelerations, because acceleration formula is g sine theta by 1 plus I by mr square, where you can directly substitute moment of inertia and find which one has got the greatest acceleration in that case. But they've asked us to compare the velocity, so you got to do it only like this. Okay, so then that's about this sum. Um, so So let's talk about the last derivation. Supposing there is a rod like this, a small cylindrical rod, in which there is a rope which is wound around, a string which is wound around, and there is a mass m which is here. This mass m, if it accelerates in this direction, there is already an mg which is acting downward. There is already a tension which is acting upward. This is going to accelerate down, the cylinder will roll. Now, can you imagine the cylinder will roll? And there is a torque that the cylinder is experiencing, and the torque itself, in this case, a torque itself is tension into radius. That sum, in this derivation we wrote frictional force into radius, a torque to be frictional force into radius here, because there is a friction here. Here there is what is providing the tension into radius, and torque is also I alpha. Hence torque into radius is equal to I alpha. Torque into radius is equal to I into a linear acceleration by radius. Therefore, the torque itself is I alpha by r square. So this is what is torque, and this is what, sorry, this is tension into radius. Tension into radius. So this is tension is equal to I alpha, and you all know mg minus tension is equal to m into a. So mg minus tension itself is I a by r square is equal to ma. Cancelling the m and m, you get an m here. G minus g is equal to a into 1 plus I by mr square. Therefore, a itself is g by 1 plus I by mr square. There is no g sin theta or anything here, because there is no inclination, right? There is no inclination in this. So, it is just g sin theta by 1 plus I by mr square. This is the way to calculate the acceleration of this. So, thus you know that find the angular acceleration of the cylinder. What you get is the linear acceleration. What I get here is the linear acceleration. Yeah, and the angular acceleration is linear acceleration by r. So it's a g by r into 1 plus I by mr square, or that value you can divide it by the radius, that's all. Okay, so that's about it. Supposing they ask you what is the tension in the string, tension T is equal to mg minus ma. Tension T is equal to mg minus what is ma? M into a itself is from here, you know, g by 1 plus I by mr square. So like that you can substitute, and you can in fact take the mg itself is common. Mg itself can be taken as common. 1 minus 1 by 1 plus I by mr square. And if you take an LCM, okay, 1 plus I by mr square. What was I doing? I am finding the tension, right? Tension itself is mg minus ma. Okay, so tension itself is mg into 1 plus I by mr square minus 1, there by 1 plus I by mr square. So I 1 and 1 get cancelled. Tension itself is mg into I by mr square by 1 plus I by mr square. And I can take this I by mr square down. It's 1 by I by mr square plus 1, you know, by dividing this each and every term by I by mr square. So this is all you have to do for finding the tension in the string. It's not so important, but still you should know these sums, you should know these derivations. This is the second part that I took today, and you have to be able to recall all the formulas in this lesson, such as the first one as you know, force is equal, torque is equal to r cross f, and you know angular momentum, torque is also equal to rate of change of angular momentum dl by dt, and then you know that torque is also equal to I alpha, and you also should know that torque is equal to I alpha. You know, power, with regard to power, you know, it should be power is equal to I omega, and then what other derivations did I do? Torque is equal to I alpha, angular momentum L is equal to I omega, angular momentum is also I omega, I1 omega 1, I did I1 omega 1 is equal to I2 omega 2 for angular momentum, yeah. So angular momentum is also an I omega. Power is also I omega. Power is rate at which work is done, dw by dt, and dw itself is torque into d theta by dt. Sorry, it's t omega. Power is t omega. Sorry, power is equal to t omega, where t is the torque into omega, L is equal to I omega. So I want you to memorize all these formulas. The kinetic energy is half I omega square. Okay, and what else? I think that's about it. And then acceleration, we got it as g sine theta by 1 plus I by mr square for a rolling down, any object which is rolling down an inclined plane. And then we also got um, um, coefficient of friction to be tan theta by 3 in the same thing. And then we also saw that cylinder which is rolling down, the acceleration for that, which is rolling, because this mass is coming down, the acceleration for that is g by 1 plus I by mr square, and so on. Okay, so this is all is the sum, and this entire chapter is over. I'd like everybody to be thorough with this.